Good morning, one and all. Welcome back to the video lecture series, Linear Integrated Circuits and its applications. This is Dr. P SREENIVASULU. Today, we are going to discuss about differential amplifier. So far, we have seen inverting amplifier, non-inverting amplifier. What is the inverting amplifier? What is the non-inverting amplifier? Voltage follower concepts. Now, the concept of operational amplifier is nothing but differential amplifier because it has two inputs. So, it can amplify the difference between whatever the voltage applied or whatever the voltage present at the two terminals, that is inverting and non-inverting. So, V0 is proportional to VD. V0 is proportional to VD. That is the concept of differential amplifier. Now, if you see the circuit diagram, it is a simple differential amplifier circuit. If you observe here, we have applied two inputs, that is inverting terminal as well as non-inverting terminal. Voltage at non-inverting terminal is V1, voltage at inverting terminal is V2, and extra there is some circuitry. This simple circuit diagram is act as a differential amplifier. Now, we need to analyze this differential amplifier circuit. Then we need to show the output voltage is proportional to the difference between the two input terminals. Simple idea is, again, we need to apply the concept of virtual ground. Now, if you observe here, what is the concept of virtual ground? The voltage difference between the two terminals. That is non-inverting terminal, inverting terminal is 0. The voltage difference between non-inverting and inverting terminal is 0. And either of the input terminals draws no current. So, these two are the basic conditions. So, here, based on the virtual ground concept, the voltage difference between the inverting and non-inverting terminals is 0. That means, suppose if you apply voltage at B is V3, voltage at A is also V3, then only the difference between non-inverting and inverting must be 0. The difference between non-inverting and inverting must be 0. And one more point, either of the input terminals, that is inverting terminal and non-inverting terminal, draws no current. Now, if you apply the circuit diagram, nodal analysis at node A, nodal analysis at node B, and equate these two, and then you will get the output voltage in terms of input voltage. That is the basic idea here. Now, you see, if you apply nodal analysis at node A, if you see here, apply nodal analysis at node A, V3 minus V2 divided by R1 plus V3 minus V0 divided by R2 is equal to 0. It is one equation. Now, second one, if you apply node analysis at node B, V3 minus V1 plus V3 minus next potential is ground potential, V3 minus 0 divided by R3. And then you write the first equation for V3 and you write the second equation for V3 and equate these two equations, you will get the, you see here, V3 minus V2 by R1 plus V3 minus V0 by R2 is equal to 0. It is one equation. At node B, V3 minus V1 by R1 plus V3 by R2 is equal to 0. And equate these two terms. And if you go for simplification, finally, if we see, it is a V0 by R2 is equal to 1 by R1 into V1 minus V2. So V naught is equal to R2 by R1 into V1 minus V2. So what is the V1 here? Non-inverting voltage. What is the V2? Inverting voltage. So finally the output voltage is, if you observe here, the output voltage is V naught. R2 by R1 is a gain factor. V1 minus V2 is the difference between both the input terminals. So that's why it is called a differential amplifier. That's why it is called a differential amplifier. The values of R2 and R1, that is our choice, that is our choice. If you want more gain, you choose R2 is greater than R1, you will get a more gain for changing the simple resistor values. Now, the another important point here we need to study the op amp problems. We have the practical op amp. Some uh, it 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 face some problems. That one type of problem is a common mode. It is a reference mode. Common mode means from the concept of this differential amplifier, if we apply voltage V1, voltage V2 is 0. We apply voltage V1, voltage V2 is 0. Whenever we apply voltage V1, voltage V2 is 0, the output V0, usually from the formula, we are expecting 0. But the output is not going to get 0. The output is not going to get 0. That is the problem in op amp. So from that, we are going to say the operational amplifier is not only depends upon the difference between the two input terminals, but also depends upon average of the two input terminals. Again, you listen, the output voltage not only depends upon the difference between the two input terminals, but also depends upon average of two input terminals. So that is the unwanted thing. The average, our designing, we have designed the circuit. The circuit design is only for difference purpose. Now, but whenever if we apply both the inputs are 0, it is going to be get some output. So what is how we are going to get this output? Usually, it is because of noise. It is because of noise. You know, whatever the noise is generated here, that is because of component circuit setup or circuit components or whatever some in the resistance, some noise is generated. It is in the order of microvolts. It is in the order of microvolts. Now, these microvolts is going to be added at the output. We are going to get, it is appear like, because the gain is very high, it is appeared some in the order of some millivolts. So it is a severe problem in operational amplifier. That's why we need to discuss here difference mode gain as well as common mode gain. One more important point. If you connect the voltage difference between these two terminals is some, suppose for V1 is 100 microvolts and V2 is some 950 microvolts. What is the difference between these two signals now? 50 microvolts. It is one case. Now, if you see the output, we are going to get some output. And the second case, if you observe, I am connecting this V1 is equal to some 100 microvolts, V2 is some 50 microvolts. Again, the difference is here 50 microvolts. But the output, if you see, in the both the cases, the difference is only 50 microvolts, but the output is not going to get same output. So based on that, we can conclude that the output is not only depends upon difference, because we have considered two cases. In the two cases, the output is, the difference is, the input difference is 50 microvolts only. But whatever the output we are going to see, that output is going to be different. So from that, we can conclude that the output is not only depends upon difference between the two input terminals, but also depends upon average of these two inputs. So that's why the output equation, theoretically we can write V naught is equal to AdVd plus, while coming for practicality, V naught is equal to AdVd plus ACVC you need to consider. But this ACVC is not desired case, it is not our, it is not in our design point of view. It is unwanted. Simply you can say that it is unwanted. So that's why we need to reject this one. So we need to reject means it is unwanted component like noise. So if you see after calculation, after designing this op-amp, if we calculate this a common mode rejection ratio, for that purpose we are going to calculate common mode rejection ratio. This AC is as well as very less value, very small value. That is our desired case here. Whenever it is a very small value, then only we are going to get our Cmrr is going to be get more. So whenever the op-amp Cmrr is more, that is a good amplifier, good op-amp. So that's why you see this common mode rejection ratio. Again, I am repeating, what is the importance of discussing about this both difference mode as well as common mode. Difference mode means in the statement itself, it is a difference mode, a differential amplifier. The design purpose is a differential amplifier. But we need to discuss about this common mode. Already I have given the clear explanation. Whenever if we connect, both inputs are 0. We are expecting the output is 0, but the output is not going to be get 0 because of some noise is present at the input terminals. Because of the noise, there may be some voltage is generated. So it is for our understanding purpose, a little bit of confusion is there because we are not applying any potential at the input terminals, but we are getting the output. We are saying that some noise. So how much of noise is added? So that noise is going to be in the order of microvolts. That's why we have taken the practical example here. We are taking the practical example. So in the practical examples, we have taken two cases. One case is 100 microvolts, 50 microvolts. The difference is 50 microvolts. Second one is 1000 microvolts, 950 microvolts. The difference is 50 microvolts. You see the statement. Even though the difference signal is 50 microvolts, in both the cases, the output voltage depends not only upon the difference signal Vd at the input, but also affected by the average voltage of the input signals. That is called common mode. That is called common mode signal. Okay, that is called common mode signal. So it is the severe problem in operational amplifier. Now finally, you write this V naught is equal to, it is a common mode gain, means average of these two signals. So you write V naught is equal to A1 V1 plus A2 V2. Here, what is the A1? What is the A1 difference mode gain? What is the A2 common mode gain? Okay. Now you can write these formulas in terms of VCM. VCM means average of these two signals. VD means the difference between the two terminals. And if you do this analysis, finally if you see V naught is equal to ADM VD plus ACVC. What is the ADM? Difference mode gain. What is the AC? Common mode gain. What is we want? Difference mode gain. What is we don't want? Common mode gain. So finally, if you write this ADM is equal to 1 by 2 A1 minus A2, difference between the two cases. What is the ACM? The average A1 plus A2. So instead of remembering this one, you write this word. It is V naught is equal to difference mode gain into Vd. It is AC means common mode gain into Vc. But we want this one. We don't want this one. So as well as possible, this common mode gain is very less. So that is our desired case. So now if you define this common mode rejection ratio, if you define this common mode rejection ratio, if you see here in the statement itself, the relative sensitivity of an op-amp to a different signal as compared to a common mode signal is called common mode rejection ratio. The name itself, it is a technical definition. Instead of remembering like this one, that just simply ratio of difference mode gain to common mode gain. Now, if you remember like this, the ratio of difference mode gain to common mode gain. it is ideally, if you take an ideal op amp, ideally it is a infinity, because in ideal op amp, the common mode gain is 0. So the common mode gain is, it is unwanted. Our desired case is common mode gain is 0. So if you calculate this common mode rejection ratio, it is going to be get infinity. But practical op amps, it is not going to be get common mode gain is 0. There may be some common mode gain is always present. So whenever it is less voltage, a less gain, so common mode rejection ratio is going to be get more. So there is no any units for this. That's why we are applying a 20 log for this. So it is going to be get some decibels. Usually our general 741 IC op amp, the common mode rejection ratio is some 70 dB. 70 dB. So it is very high common mode rejection ratio value. It is for general op amp. Now see one simple problem is here for calculating this common mode difference mode gain or common mode gain. Not necessary. So today I am going to stop this class. We will see in the next class, the next topic.